Welcome to 2.6. Today we're going to talk compound interest. Here are the learning objectives for 2.6. Make sure you read them and get them written down before moving on. Here's the question for the lesson. Make sure you pause the video and read it before moving on. In 2.6, we're going to talk about using the compound interest formula, which is right up here. A is equal to P times 1 plus R raised to the T to find the new balance given after a given time. Okay, so in the last section we discussed the importance of interest. It is not only big business for banks and investors, but as a way of securing a comfortable retirement and reaching financial goals. Understanding interest helps you to make the best decisions. The last section dealt with simple interest, which illustrates the basic idea of interest. In most cases in the real world, however, we don't use a simple interest formula to calculate interest, but we would use a compound interest formula instead. Again, that's that P times 1 plus R raised to the T. Basically, this formula accounts for the fact that as you invest and earn interest, your balance grows. You are not only due interest then on your original balance, but on the new balance, which includes the first installments of interest. You get paid interest on the interest. Okay, so let's say you invest $100 for 3 years at 10% interest. After 1 year, you'd have the original amount plus 10% added on, so you'd have $110. Then in the second year, you still get that 10% interest, but not only on the $100, but on the $110 that's there now. So instead, you'd earn $11 interest and you get $121. Third year, you would earn 10% of $121, which would be $12.10. So your ending balance would be $133.10. You got paid interest on top of the interest that you made in the previous years, and that makes a difference in your final balance. And so the example that was above there, that shows compounding every year. That means you get paid interest once a year on your balance. In the real world, interest is sometimes compounded monthly or daily. For compound interest, we'll use the formula A is equal to P times 1 plus R raised to the T, where A is your final balance, B is your principal amount, R is your interest rate as a decimal for the period, so daily, monthly, semi-annual, annually, etc. And then T is the number of time periods for which the money is invested. Okay, so if we're compounding occurs monthly, there's going to be 12 compounding periods per year. So in the example above, my principal was $100, my interest rate was 10%, and T was 3 since there was 3 times that it got compounded because it was once a year for 3 years. So if you substitute those values in for the formula, 100 in for P, 0.10 in for R, 3 in for T, and we still get 133.10. So the most common compounding periods that we will see annually, that means it happens once a year, so you take 1 times the number of years that it's compounding. Semi-annually happens twice a year, so however many years that it's getting compounded for, you would multiply that by 2 to get the semi-annual number of periods. Quarterly is 4 times a year, so 4 times as many years as it's going for. Monthly is 12 times a year, so 12 times the number of years. Daily is 365 times a year, so you do 365 times the number of years. So our first problem, what is the final balance on a savings account that earns 4.5% interest per year that is compounded annually, which again means once a year, for 9 years if the beginning balance is $2,500? Okay, so $2,500, that's our principal, because that's what it starts out at. Okay. Our interest rate is 4.5%, so writing that as a decimal is 0.045. Annually for 9 years, so once a year for 9 years, that means our T value is going to be 9. So when we do this, we do the parentheses first. 1 plus 0.05 gives us 1.045. We're going to raise that to the 9th power first. So to do that on your calculator, the first thing you would do is you plug in 1.045. Then you would look for the button that looks like this in the middle on the left side of your calculator. Okay, that's called the exponent button. Then we'd hit 9, and we would get that it's 2,500 times. We'll go 1.48609514. That's what we see on our calculator. Then we can go ahead and take that times 2,500. and we would get that it was about 3715.2. We're gonna say 4 because we're talking in terms of money, so that 3 gets rounded up by the 7. So our next problem, we got $40,000 invested in a retirement account. So 40,000 is our value for P. Alright, now this is where it gets a little different, because if you'll notice, compounded monthly interest rate of 6%. So what that's going to do for our R is we're going to take that 6% and we're going to divide it by the number of compounding periods. So it's going to be 0.06 over 12. Okay, and then we've got 2 years compounded monthly. 2 times 12 gives us 24. So T is going to be 24. And we can go ahead and type that into our calculator the same way we did before. And if we type in what's inside the parentheses first, if you do 0.06 divided by 12 plus 1, you get 1.005. We raise that to the 24th power, and we get 40,000, sorry, times 1.127159776. Then we multiply that by 40,000, and we get $45,086.39. So the next thing is we're gonna compare balances after a certain amount of time with the same rate of interest, and simple interest versus compounding interest. So we're going to be comparing those two. So we've got the first account is simple interest. I've got the formula written there. The second account is compound interest. We've got the formula there. Go ahead and pause the video and plug these in and solve before hitting play and seeing how you did. So as you can see, if we do the simple interest formula, we would earn $32,000 over that 20 years. We add that to the original $20,000, so we get a total of $52,000 total. Compound interest, if we do that, we would end up with a total of $93,219 at the end of the 20 years. So you can see it's a lot different when you're just taking the interest of the principal every time, or if you're taking the interest of the total with interest included each year. Now we're going to use the same interest rate, but we're going to compound it over different periods over the same amount of time. So it's going to be the same amount of years, but we're going to compare a different number of compounding periods. So for this example, we're going to take $15,000 for 10 years in a bank that pays 6% compounding annually versus compounding daily. And so what we'll need to do is we'll need to do them separately. Go ahead and pause the video and give it a shot first before hitting play and seeing how you do. So for annually, our equation should have been 15,000 times 1 plus 0.06 raised to the 10th, and we would have gotten a total of 26,862.72. For daily, the difference here is when we take our interest rate, we divide it by the number of compounding periods a year, so it would be the 0.06 divided by 360. And we would also take our years times the number of compounding periods. So that would mean our exponent is 3650 there. So we'd have 15,000 times 1 plus 0.06 over 365 raised to the 3650th power, giving us a total of $27,330.43. So we gain an extra roughly $500 compounding daily versus annually. Pretty much all these examples have been real world problems. We use it a lot for interest rates, savings accounts, investments, stuff like that. So make sure when we're doing this, we give a real world answer to, we're rounding it to the hundredths place because we are talking about money. But sometimes more decimal places are needed so that the numbers are accurately, while in yet other cases having too many decimals is cumbersome and unnecessary. Okay, so we've got two investment options here. We're both going to start with $10,000. We're going to invest it for 10 years. But in option 1, we want to do a 6% interest rate compounded monthly. And in option 2, we're going to do an 8% simple interest rate. We want to know which one is bigger. So go ahead and pause the video, solve these two problems, then hit play and see how you do. For the first option, our equation should be 10,000 times 1 plus 0.06 over 12, because again, it's compounded monthly, so we need to divide our interest rate by 12. Raised to the 120th power, because again, number of years times the number of compounding periods per year. 10 times 12 is 120. If we type that into our calculator, we should get $18,193.97 at the end. Option 2 is simple interest, so I is equal to PRT. Plugging in our values, we have 10,000 times 0.08 times 10, because it's 8% interest rate. That means the interest gained is 8,000, so we take that 8,000, add it to the original 10,000, and we get a total of $18,000. So if you'll notice, option 1 gives us an extra $193.97. So this option 1 is the better deal. Here's the completed example from the beginning. Go ahead and read through that before moving on. So just to review, keep in mind when calculating compound interest, it's very important to use the formula accurately. So compound interest, the formula is A equals P times 1 plus R raised to the T. A is our final balance. P is our starting amount or principal amount. R is our interest rate per period. So we take our interest rate and we divide it by the number of compounding periods per year. T is the number of time periods. So we take the number of years times the number of compounding periods per year. So make sure we keep that straight. R and T are different in compound interest than they were in simple interest.